In this video, we will solve a problem in details regarding the concept Bohr model of the hydrogen atom. It's level AP, chemistry AP. Let us start. Consider the Bohr model of the hydrogen atom. Calculate the change in energy when an electron in level n equals 6. So this is the initial one. Return to the ground state and final equal 1. According to the Bohr model of the hydrogen atom, delta E, the formula for the energy, delta E equal minus 2.178 times 10 negative 18 joule, 1 over n square final minus 1 over n square initial. So simple substitution, minus 2.178 times 10 negative 18 square final, it means 1 over 1 square minus 1 over 6 square. The final answer is minus 2.117 times 10 negative 18, and the unit is joule. Is the answer convenient? Yes, simply because it's in negative. And as we know, if we have these energy levels, n equal 6, n equal 1, and if the electron initially it was on level 6 and go down from high energy level to low energy level, we know that energy is released in such a case. Energy is released, so the answer is convenient. Now part B, calculate the wavelength of photon released. There are relations between energy frequency and wavelength such that we can calculate. We know that delta E equal h nu, the frequency. But nu is related to wavelength, c equals c over lambda, while h, it's the Planck constant, which is equal 6.626 times 10 negative 34, and c, it's the speed of light in vacuum, which is 3 times 10 to power 8 meter per second. This is joule second. Okay, so let us do simple substitution. Delta E equal h nu equal hc over lambda, which is equal 6.626 times 10 negative 34. And delta E from part A, we found that we will take it without negative value because the wavelength always positive, times 10 negative 18 times 3 times 10 to power of 8 all over lambda. A simple calculation to find that lambda is 9.4 times 10 negative 8, and the unit is meter. Supposedly he asked you to change it or to calculate it or to write it in nanometer. We know that every 1 meter equals 10 negative plus 9 nanometer. So I can change the unit. 9.40 times 10 negative 8 meter. I will multiply 10 to power 9 nanometer over 1 meter, meter cancelled, and the final answer is 94 nanometer. Moving to part C, what is the energy required? Again, asking about the energy. So what is the energy required? Delta E equal how much to excite the hydrogen electron from n equal 1, so this is the initial, to n equal 6, this will be the final. Again, the same formula for Bohr model. Delta E equal minus 2.178 times 10 negative 18, 1 over n square final minus 1 over n square initial, minus 2.178 times 10 negative 18, 1 into 1 over 6 square minus 1 over 1. Here the final answer will be 2.117 times 10 negative 18. Is the answer convenient? Yes, it's positive, since the electron excited from low energy to higher energy. If these are the energy levels, this is 6, this is 1. Here in this problem, the electron, it was here and going to higher energy level. So in such a case, the energy should be absorbed, indicating that the sign is positive. Now, part D, calculate the energy required to remove an electron from a hydrogen atom in its ground state. To remove the electron. Removing the electron, it means taking it out from the atom, so energy, it will be infinity. This will be the final. So remove it from its ground state, so N initial is equal to 1. So delta E equal minus 2.178 times 10 negative 18, 1 over N square final minus 1 over N square initial, which is minus 2.178 times 10 negative 18, 1 over infinity square, which is equal to 0, minus 1 over 1. So the answer will be 2 minus times minus, and the answer will be plus 2.178 times 10 negative 18. Again, the answer is convenient with its positive sign because the electron, it was here, energy level 1, and got removed completely. Let us say if this is N equal infinity, got removed, so the energy should be absorbed. Now let us see what will happen if I'm talking about helium atom. The first question, can the Bohr model be used to calculate ionization energy of helium? Okay, when we discussed and studied before Bohr model, we know that the Bohr model discusses and gives the energy for hydrogen atom or hydrogen-like atoms, that they have 1 electron. In reality, helium has 2 electrons, unlike hydrogen. So they have 2 electrons, unlike hydrogen. So because of this, and Bohr model doesn't count actually the shielding, electron shielding effect, because in Bohr model only 1 electron present. So simply cannot be used to find the first ionization energy of helium, but it can be used to find the second one. Why? Because the second ionization energy, helium plus, there will be only 1 electron, 1s1, which will be exactly like hydrogen. So the answer, the Bohr model of the hydrogen atom cannot be used to describe the energy levels of multiple electron systems, as we said, which is more than 1 electron. Why? Because it doesn't count the electron shielding, since it doesn't account electron shielding. So no, the answer is no, because the Bohr model. However, it could be applied for the second ionization. However, it could be used to calculate the second ionization energy, i.e. 2, which is the second ionization energy. Double I, would you expect the ionization energy for helium to be higher or lower than the value calculated in part D? If we have to go to part D, in part D, this was the energy calculated, And if, as you see, it was removing the electron. It was removing the electron. So in part D, the energy, it was 2.178 times 10 negative 18 joule. So would you expect the ionization energy for helium to be higher or lower than that, the value in part D? In part D, we are talking about hydrogen. If I want to talk about helium, to remove electron from helium, as we said, the helium has 2 electrons, 1s2. So it has 2 electrons, and these 2 electrons are not completely shielded from the effect of the nuclear charge, which is +2. Nuclear charge, which is +2. So it's not completely shielded. So there is a bond between the electron and this high nuclear charge, which is higher than 1, which makes it difficult. So we to remove the electron. So we expect the ionization energy to be higher. So we expect it to be higher. We expect it to be higher than of hydrogen, because the valence electrons in helium are not completely shielded from the higher +2 nuclear charge. Triple I, calculate the ionization energy for He+. Would you expect this value to be higher or lower than ionization energy of helium? Let us see. First of all, can we calculate the ionization energy for He+? Yes, the answer, because simply He+, it's a hydrogen-like atom, because He+, its electron configuration is 1s1, because plus removed 1 electron, so it is equivalent to the hydrogen. So yes, we can. Let us calculate its energy. Delta E equal minus 2.178 times 10 negative 18, but this time instead of 1 over n squared final, it will be 2, because here the electrons are 2. So 1 over n squared final minus 1 over n squared initial. So for ionization for plus, it means that an initial ground state, and we want to remove the electron completely. We want to remove the electron completely. So n final will be infinity. So let us substitute. Delta E equal minus 2.178 times 10 negative 18, 1 over infinity square, 2, as I said, should be 2. I wrote it 1, should be 2, because the number of electrons 2. So 2 over infinity square minus 2 square over 1 square. And the answer will be plus 8.712 times 10 negative 18 joule. Again, it's convenient because it's positive and energy is required, so it should be absorbed to remove the electron. Now, would you expect this value that I obtained, 8.712 times 10 negative 18, do I expect it to be higher or lower than the ionization energy of helium? If I want again to consider in helium has 2 electrons, so 1s2, so 2 electrons. Here in helium plus there is only 1 electron. So if I want to remove here this electron from this one, there will be I'm not considering in such a case the electron-electron repulsion, because they are here in the same. I am considering electron-electron repulsion because here in the orbital the two electrons are together. So there is electron-electron repulsion, which helps in removing the electron. So which makes the ionization energy for helium lower than that for He+. So this value I'm expected it to be higher. So value expected to be higher since there is now in He plus no electron-electron repulsion competing with the strong attraction to the nucleus. Okay, so this is what I wanted to discuss in detail, this problem. But back to part C, also I can solve it in different way if you want. This way is always applicable. If you want, I can relate it to the one in part A, because in part A it was removing an electron from, electron is lowered from n equals 6 to ground state. As you see here, opposite, from n equal 1 to n equals 6. So without calculation, if you want, I can directly say, so it's the opposite. So just I write opposite sign with the same value of